Okay, so this is kind of the second part of this attempt to run this at 150 megahertz. And, definitely there's a pile of healthy skepticism on whether this board could achieve that. And I guess to some extent I share that. But anyway, what I'm going to do in this video is obviously the first part, I've got the power supply circuitry together. The first part is to confirm that I can get a stable and good 150 megahertz quadrature signal out of this LO here. Obviously, if I can't get that, I'm not going to proceed any further. But so I've got the si5351 board installed on the Tayloe detector. I do have to connect this board up to an ESP32 so I can drive this. And so that's what we'll be doing next, get it hooked up to the ESP32 and see if we can generate that 150 megahertz LO signal. Okay, so here's the Tayloe detector board with the si5351 hooked up to the I2C interface, one of the I2C interfaces on the ESP32. And just to cut to the chase, if you have a look here, I have been able to achieve a stable quadrature signal at 150 megahertz. So that's the good news. The bad news is I had to do quite a bit of hackery to get there. So I thought it might be interesting to just sort of walk through and do a bit of a refresher on the si5351, how it works, how you configure it, and what sort of hackery I had to do to get it to emit a quadrature signal at 150 megahertz. Now, one of the things that was really helpful in this analysis was, and I'll include a link to it, a site called rfzero.net or .com. I can't recall which it is, but I'll include a link to that site below. But anyway, let's just do a bit of a refresher on the si5351. I can walk you through some of the code changes I had to do.
Okay, so here's the si5351 block diagram. And just a note, I did get this diagram from this site here, rfzero.net/tutorials. It's a great page that describes in a lot of detail how the si5351 works. But anyway, from sort of the our perspective, there's three major components involved here. There is the VCO, and you'll hear this sometimes referred to as the PLL. And you can see here's that phase lock loop right here. There is the reference crystal, and that's typically either 27 megahertz or 25 megahertz, and that will be used in the sort of the computation of the PLL frequency. And then finally you have the this is referred to as OMD here, but it's referred to in the documentation as the multi-synth. And then finally you have on output, this is optional here, a divider which will take this frequency and divide it by a series of integer values. Okay, so the way the si5351 works is it's governed by these two equations right here, where FVCO, also known as the PLL, is basically the reference crystal frequency, which is right here, multiplied by these three parameters here. And these three parameters are what you feed into the, this is how you program the si5351. So it doesn't use floating point math to compute these. It all uses this sort of fractional math here. So basically you pick an A and a B and a C where the reference crystal 27 megahertz multiplied by that gives you the desired PLL frequency. And this is a bit of theory. We'll go through a worked example on the following slide. And then the next step is once you've derived this PLL frequency, the output frequency is governed by the PLL frequency divided by, again, three integers D, E, and F here. So it's all a bit confusing and counterintuitive, at least it is to me. So let's go through a worked example here so we can see how A, B, C, D, E, and F are derived. Okay, so let's take an example here where the ask is to basically output here a 20 megahertz signal in quadrature. So the interesting thing about this is you kind of work backward from the multi-synth back to the desired PLL frequency. But let's just go through that. So the first thing you want to do is basically, in order to produce a quadrature signal, and this is just part of the limitations of the si5351, this VCO multiplier right here, D plus E on F, needs to be an integer. So the goal is, and effectively, because this needs to be an integer, E would be 0 and kind of F we don't care about. But once we've picked that integer, that multiplier D, you've got a limitation that multiplier D, when multiplied by the desired output frequency, 20 megahertz, needs to result in a number between 600 and 900 megahertz. And that basically is one of the limitations of the si5351, is the PLL operates between this frequency and this frequency. And additionally, because we want a quadrature output, that number should be even. So let's say, for example, we're going to pick 30. We could pick 40. That would fall in the range too, and that would be equally valid, but let's pick 30 for this example. One other limitation is the documentation says that this number that you pick in order for it to work should be greater than 6. Although in my testing, I couldn't get it below 6. Anything below 8 as the minimum wouldn't produce a quadrature output. Okay, so we've got our multiplier D here, which is going to be 30. And so the next step is to basically, now we've got a VCO frequency of 600 megahertz. So the next job is to derive A plus B on C, such that the reference frequency, 27 megahertz, multiplied by A plus B on C gives us 600 megahertz. So just going through that, the first step is to pick A, and A is easy. It's basically, you just do integer division of 600, the desired output frequency, divided by 27, the reference frequency, and that'll give you 22. Now, C can be a number up to, I believe, 2 to the 32. So what we pick here for maximum resolution is 1,000,000. And then finally, B is governed by this equation here, VCO frequency mod the reference frequency multiplied by C divided by the reference frequency. And what that will give us is 222,222. So the final A plus B on C is 22 plus this number divided by 1,000,000. So that's basically, that's effectively the floating point number, 22.222222. And if you take 600 megahertz and you divide it by 22.222222, you'll get 27 megahertz. Okay, so at this stage, what we've got is 20 megahertz on the output here. Now, the final part of this is to output 2 signals in quadrature, and this is where the it gets even stranger. So basically, there is a set phase function in the EtherKit toolkits, but what that basically does is the number that you pass to that isn't degrees offset or anything like that. What it is in terms of is what a quarter cycle is of the PLL. So in other words, because the output frequency is a multiple of the PLL, an integer multiple of the PLL frequency, you use that same multiplier and you pass that to set phase. So the multiplier that we chose at the beginning here of 30, that's the integer that we pass to the set phase function. And there's a lot of limitations on what that integer can be. It has to be an integer that's less than 127. And as I said before, I couldn't get it working less than 8. So 8 was the minimum that I could get there. So I know this was certainly confusing to me. Have a look at that rfzero page if this still doesn't make sense, or drop me a comment below. It is super counterintuitive. It's a lot more complicated under the covers than you think. Now, both the toolkits, there's an EtherKit toolkit, and I believe there's an Adafruit toolkit, hide a lot of the details from you. So in other words, you can call set frequency in the EtherKit toolkit, and you'll get the desired frequency on output. The problem with calling set frequency is it will pick for itself what A, B, C, D, E, and F are, and then you won't be able to derive a quadrature output. So there is a function called set freq manual in the EtherKit toolkit, which you can use to basically put in a PLL frequency and an output frequency and derive the multiplier that way. Unfortunately, and this is also a part of the challenge, it doesn't seem to work much beyond 100 megahertz. So I'll show you some hacks that I've done in the code that allow at least up to, unfortunately, but not including 150 megahertz exactly. I'll show you those hacks that I've done in my fork of the EtherKit toolkit. Okay, so this was basically the main change that I made, and this is in my sort of private fork, and I don't plan on doing a pull request of EtherKit because this is Hackery. But basically, one of the challenges was this is that PLL bounds checking. So this is where it says the PLL frequency needs to be between 600 and 900 megahertz. Now, you can overclock the PLL, and the PLL maximum frequency is actually 1.2 gigahertz. And so in order to meet the combination of the minimum multiplier being 8 and getting it up to around about 150 megahertz, what I need a PLL running at is close to 1.2 gigahertz. So I had to remove this check right here in order for that to happen. So that's basically the hack that I did. I did actually try, there's another place in here where it checks to see if the frequency you ask for is greater than or equal to 150 megahertz, which is what this div by 4 freq is. This didn't seem to work though. So what I've been able to do is be able to go up to, but not including 150 megahertz, and get that output in quadrature. I can go over that, but what I haven't been able to do is go over that frequency up to say 160 megahertz and have that have a quadrature output. So it looks like, well, at least as far as I can tell, that does look like to be a limitation of the si5351. You can go right up to 150 megahertz, you can get a stable quadrature output, but you can't go greater than or equal to 150 megahertz. And that's what you saw on the oscilloscope. So anyway, that's the changes I've made to my fork. What I'm going to do now is, so I have been able to get close to 150 megahertz in stable quadrature output. So what I'll do is I'll go back to the Tayloe detector board, and I'm going to start with 40 megahertz. Just confirm that I'm getting a good audio output at 40 megahertz at a 40 megahertz RF signal, and then I'll slowly increase that up to 80, 100, 120, and so on and so forth, and we'll see exactly where the Tayloe detector stops working.
Okay, so I'm ready to continue with trying to get this Tayloe detector working at 150 megahertz. And my apologies, I've been dragging my feet on getting this video out there. But anyway, we're ready to test. So here's the Tayloe detector board before fully populated. There's the splitter, there's the FST3253, and the output capacitor resistors. So what I'm going to do is I'm going to first test it at an LO of 20 megahertz. And I'm going to be injecting a signal from my signal generator up the top there. And just for the purposes of the test, I've bypassed the bandpass filter, because obviously this is a 150 megahertz bandpass filter. So 20 megahertz coming in here, and then what I'll do is I'll go up in 20 megahertz increments to see if we can get the Tayloe detector working all the way up to 150 megahertz. We'll see where we go anyway. So this is basically at an injected signal of 20 megahertz plus 1 kilohertz. So you can see here we've got the, this is the output that I'm sampling, the I and the Q signals. So you can see I've got a nice mixing product there at around about 1 kilohertz. And there's those I and Q signals. Now just to confirm that they're correct, as you notice, this is actually an upper sideband signal here. So you can see purple is leading yellow. If I go below 20 megahertz, let me go 1 kilohertz below 20 megahertz. Bear with me while I get there. You will see that now yellow is leading the purple trace. And again, we've got a 1 kilohertz signal there. So that confirms the Tayloe detector is working at 20 megahertz. Let's pump it up now to 40 megahertz. Okay, so now I'll just pan up to the signal generator. You can see we're at 40 megahertz plus 1 kilohertz. And if we, and I've reflashed the board to be using a 40 megahertz LO. And as you can see, I've still got that nice, those nice I and Q signals there. Let me do the same test as before. Go below 40 megahertz, 1 kilohertz below. And as you can see, it's all working fine. Although, interestingly, there's an increased amplitude difference between the I and the Q signals. So I'm not sure if that's a measurement artifact or whether that's actually something real in the circuit, but interesting nonetheless. So let's go up now to 60 megahertz. Okay, so now we're up to 60 megahertz. As you can see, I did forget to mention I'm injecting a minus 50 dBm signal here. So 60 megahertz plus 1 kilohertz, and as you can see, I've still got that nice I and Q output there. At around about 1 kilohertz, although the difference is increasing. I'm sure that's to do with the kind of the discrepancy in the input crystal frequency, though. But as you can see, nice stable signal there. Although the amplitude of the signal is certainly diminished from that earlier 40 megahertz signal. Let me do the same test again. Let me go below 60 megahertz, so kilohertz below. And you can see there, I'm now at 59.999 megahertz, and it's still working pretty well. Let's now go up to 80 megahertz. Okay, so we're up at 80 megahertz plus a kilohertz. And as you can see, unfortunately, we're starting to get a breakdown in the output there. As you can see, one of the audio output signals is relatively stable, but the other one has all this jitter in it. So not looking good for 150 megahertz, I will say. So let's go up now to let's try 90 megahertz and see if the signal deteriorates further. Okay, so we're up at 90 megahertz now, and you can see the output signal is. Well, let me just adjust the oscilloscope there. Sorry, wrong channel. Although the output audio frequency is okay, you can see we've got a significant difference between the amplitude of the I and the Q channels, which obviously is pretty catastrophic for an IQ style radio. So it looks like the this Tayloe detector, at least as configured here, is not going to work much past 80 megahertz. Now, interestingly, I did have a comment from someone who said he had tried it and he couldn't get it working past 75 megahertz. So this is pretty much a confirmation of that. So I guess, unfortunately, we can call the trying to get this Tayloe detector working at 150 megahertz as a fail at this point. Unfortunate, but it is what it is. I'll do one more test at let's say 100 megahertz, and then we'll call a wrap. Okay, so here's the test at 100 megahertz, as you can see. Let me just pan up so you can see that. 100 megahertz plus a kilohertz. And the si5351 on the Tayloe detector is running at 100 megahertz. So we are seeing some kind of a signal out here. This does have a frequency of about a kilohertz, this purple trace. But as you can see, we don't have IQ audio on output. We don't have that signal in quadrature. So this is definitely a fail at this frequency. So I guess the upshot is the Tayloe detector will work somewhat up to around about 60 megahertz. Beyond that, it doesn't really work at all. So we'll chalk this one up to being a failure. I know there was a pile of healthy skepticism on the channel about whether this could work, and that skepticism's been borne out. And I think one of the commenters mentioned that the maximum switching frequency of the FST3253 simply isn't high enough to be able to run it much beyond 60 to 70 megahertz. So that was proven out. We'll chalk this one up to being a failure. I did want to go ahead and do it. I was kind of intrigued whether it could work. So there you go. 60 megahertz is about the tops you can do, and any more than that, and it's probably not gonna work. So anyway, I'll wrap this for now. I hope to continue the SDR transceiver series shortly. I've got the receiver sort of all ready to go. It's just a matter of getting the videos out there, and I hope you enjoyed this little diversion. That's all for now. Catch you later.